optimization. We're ready for this. We know enough about derivatives and how to understand word problems. We're ready to maximize or minimize something, and that is what optimization is. So it's optimization basically is finding the values which will be optimal to use in your situation given your limitations. So the values optimal means we're going to maximize or minimize something. Often we maximize a volume or an area, or we minimize a surface area or minimize cost. Given the situation, we're going to optimize it, make it biggest or smallest according to what we need to do. So that plays into how to find maximums and minimums that we've been talking about in chapter 4.3. Mostly we're finding where function increases or decreases, relative maxes and relative mins. Or you could also apply the closed interval method, because there's limitations given with this. These are practical problems where we have limited amount of time and space and resources. So you could also use the closed interval method. So I'm going to be doing it with the first derivative and finding relative maxes and mins. You can look in your book and see how they approach it from a different way by looking at the constraints of the problem, and either way is fine. On page 330 to 331 of your text, they give you the steps to solving optimization problems. I'm not going to write those steps out, but you will hear me going through them as I work each problem. Okay, so in each situation, you'll have the limitations that they give you in the problem. That is referred to as the constraints of the problem. So in each of these problems, or in most of them, it's really easy to say, okay, this equation is my optimization problem. This is what I want to maximize or minimize. And this is my limitations. These are the constraints I have to work with. So sometimes I'll refer to those, and in most of these situations, it kind of flows into that pattern. The first one it's not a very practical problem, but it gives us an idea of how this goes, and then we can dive into some more practical examples. Number one, the sum of two positive numbers is 16. What is the smallest possible value of the sum of their squares? That's what we have to figure out. Okay, so number one, the sum of two positive numbers. What we want to do here is name some variables. So I have two variables. I'm going to name one x, and it's got to be positive. And here's my other number, y. These are my two positive numbers that I've named. And what it told me is that the sum of these numbers, when you add them together, it is equal to 16. This is the truth. This is a constraint. This is a constraint. There's no changing that. We don't optimize, we don't make this maximum or minimum. This is just the truth. When you add these numbers together, it's got to be 16. Okay, so you could go through 15 plus 1, 15.9 plus 0.1. There's an infinite amount of combinations. We have to find the combination where this is true, but the sum of their squares is, let's see, they want it to be the smallest. So the sum of their squares, this is it, x squared plus y squared. This is the sum of the squared. This equation right here, and what am I going to call this? I'm going to call this the sum of the squares of squares. I'll put a different, I'm just going to use words right now. The sum of the squares equal to this. This equation is called the optimization equation. This is what I want to optimize. And in this particular case, I want it to be the smallest. So I want to minimize this equation. Okay, so basically this is the constraint equation. This is the optimization equation. This is what I want to find the smallest of. Okay, what you do in general is use the constraint, the truth that you're given, and rewrite one variable in terms of the other. It doesn't really matter which you choose. So pick a variable and get it by itself. So over here, I'm going to choose to solve for x. Since I decided that it didn't matter, I'm going to move y to the other side by subtracting him. What do I do with this? I use this knowledge to rewrite the constraint into terms of one variable. So since I solved for x in terms of y, I'm going to just substitute this in for my x. And so that gives me a nice equation. Now, since I've made that decision to write all of this in terms of y, I'm going to abbreviate this into s of y because it's a function of y. You don't have to do that, but it makes it easier for me to think about this, so I do that. 16 minus y squared plus y squared. I just made that substitution. Now I have one equation all in one variable, and I can work with that. Let's square this. S of y is equal to 16 times 16, which is 256, minus 32y plus y squared plus y squared, okay? S of y is 256 minus 32y plus 2y squared. This is the sum of the squares equation in one variable, and I want to minimize this. Okay, we learned how to find maxes and mins. You take the derivative, and then you find critical values, and then you do a test and say, where is it max, where is it min? So let's go through that. Let's take the first derivative. That's going to be negative 32 plus 4y. Take the first derivative. When you set this equal to 0 and solve, you find critical values. So let's do that. 4y is 32, y is 8. Now let's do this little test. What happens around 8? We're going to plug some test values into the derivative. So I'm going to pick something like 5 and something like 10 here. And so, because these are both positive numbers, I'm going to let y be this and see what happens. Okay, well, when y is 5, I will plug it into the derivative, right? 5 times 4 is 20. Negative 32 plus 20 is a negative, okay? This is decreasing at this point. If I put in 10 for y, 4 times 10 is 40, minus 32 gives me a positive. This is increasing. What I found is that there is a relative min at 8 when y is 8. That's the test I needed to know. 8 is a number that's going to help me out here because I'm trying to minimize this function. That's what I needed to know. So what y equals to 8 gives me the smallest. So what would x be in that situation? Well, when y is 8, x is 16 minus y, x is 8. When x is 8 and y is 8, the sum of the squares is at its smallest. And so that's the answer to this one. So that was kind of one to warm us up. Now we're going to look at some more practical situations. How about number 2? This is a nice one about a farmer. It says a farmer with 750 feet of fencing wants to encircle a rectangular area and then divide it into 4 pins with fencing parallel to one side of the rectangle. What's the largest possible total area of the 4 pins? Okay, so the first example, I did not draw a picture because it was just numbers. But I am going to try to draw a little picture here just to label my stuff and see what's going on here. It says, a farmer with 750 feet of fencing wants to encircle a rectangular area. So I see a rectangle. Here is the area he wants to encircle. So draw some kind of a rectangle. It doesn't matter what shape you make. Make it a rectangle, but it doesn't matter if you make it this way or elongated this way or square. Pick a rectangle. Draw something. And then it says divided into 4 pins with fencing parallel to one side of the rectangle. So you got to divide this. On my paper, and I'll just show you this. I'm going to do it maybe differently just to show you it doesn't matter. Do you see how I did it long ways that way? I made 4 pins that way. I'm not going to do it that way. Now I'm going to divide it this way. It doesn't matter. I have to make 4 pins. It doesn't even say that these have to be the same size, does it? That's just naturally how I went. But I made 1, 2, 3, 4 pins that way. So draw yourself a rectangle, make it 4 pins. We are going to calculate what size it should be. What I'm drawing here is not the end product. This is just something for me to label information. And so that's what we're doing here. Now it says, what is the largest possible total area of the 4 pins? So we are limited by the amount of fencing that we have. That's our constraint. So what they said is we have 750 feet of fencing. Let's think about this. This is a practical problem. This is fencing right here. So I'm going to label this moving in the left-right direction as my X. This side of the fencing is X, and this side of the fencing is X. And then we have these tall pieces here, and I'm going to label these pieces Y, but each piece of this is a piece of fencing, right? You would physically have to go put this fence in, so you have to buy that product. So how much fencing would we have to use here? Well, we need 2 pieces that are X in length. We need 1, 2, 3, 4, 5 pieces that are Y in length. So this represents the total amount of fencing that we're going to use, and the constraint is that the total amount of fencing is 750 feet. That is what we're stuck with. That's all we get to use. All right, what do we want to do with that? We want to maximize the area. Well, the area of a rectangle, here's just a little length times width. The area is the length times width, right? In general. So for our picture, the area is still length times width, X times Y. We want this to be as big as it possibly can. We want to maximize this. This is the optimization equation. This is the constraint. So we want to optimize this. We want to maximize this, in fact. All right. What we're going to do the same thing we did before. We're going to go to the constraint, the truth, what we're stuck with. We're going to write one equation, one variable in terms of the other, and then plug that into this guy. So let's do that. I think last time I solved for X. This time I guess I'll solve for Y. So I'll say 5Y is equal to 750 minus 2X. Now it doesn't matter which one you solve for, but pick one and do it. So now divide both sides by 5. 5 goes into 75. Where's my calculator? I'll just have to do it this way. Sometimes I just have to use my brain. 5, 25 is 5, 25, 150. 150 minus 2/5 X. All right, that's fine. I'm going to use this. Now I'm going to make this substitution in here for Y. So now A of X is going to equal to X times Y, which is 150 minus 2 over 5X. So A of X is 150X minus 2/5 X squared. Okay, we want to find the values of X that would maximize this. All right, so take the first derivative. That gives us 150 minus 4/5 times X. Set this equal to 0 to find the critical value. So we get 150 is equal to 4 over 5X. Let's see here. Let me multiply both sides by 5 to kill the fraction. Times 5 times 5. And I get 4X is equal to 150 times 5. Oh, that's the same thing. 750. I guess that makes sense, right? I just divided that by 5. 750. Now we'll divide both sides by 4. All right. 4, 35, 8 times 4 is 32. 3. Oh my goodness, I should have brought my calculator. I'll have to double check this real quick. That's a 2 times 4 is, no. That's a 7 times 4 is 28. 205. 1875, is that right? Let me just check if this is looking okay to me. Yeah, except I think I'm off a decimal. Let's see, where's my decimal supposed to be? This is 750, here's my decimal. Yeah, that's the wrong place. 187.5 is X. So let's test this. 187.5. Let's pick something lower than that. I'll pick 100. Let's pick something higher than that. Let's pick 200. Let's plug that into this equation. All right. 100 goes in for X. And let's see if we get a positive or negative out. That's all we're testing. So if we go to right here and I stick 100 in for X, what's going to happen? 5 goes into 100 20 times. 4 times 20 is 80. 150 minus 80 gives me a positive. Okay. 200. 200. 5, that's a 40. 40 times 4 is negative 160. 150 minus 160 is negative. That's decrease. So So we find that when x is 187.5 feet, right, we get a maximum. And we wanted to maximize that, so that's good. So what would y have to be? Well, y would be 150 minus 2/5 times 187.5, and we find that y would have to be 75 feet. And x is this. And what would the maximum area be? The max area would be x times y. And so I already did this. It's 14,062.5 square feet. And so that would maximize the area of that pen. I did this completely opposite than I did the other way, but you get the same numbers. It doesn't matter. Let's do number 3. This is good. This is a box with an open top. So let's see how we could form this. So, looking to see if I have, oh, I do. Okay, this will be good. Okay, so let's read the problem. I'll try to give you like a little visual of what is happening here. So, it says a box with an open top is to be constructed from a square piece of cardboard, 3 feet wide. By cutting out a square from each of the 4 corners and bending up the sides, find the largest volume that such a box can have. So let's think about this. We have a square piece of cardboard. So here is a square. This is my square piece of cardboard. And so they're going to form a box that doesn't have a top by cutting out little squares in the sides. And so they're going to take a little bit of, they're going to cut this out. Little square. They're going to cut out a little square in the sides. And so once they cut these little pieces out, then they're going to fold up these sides, okay? They're going to fold up these sides, and it's going to make a box. So let me just show you a visual. This is not a square, but this is like a note card, okay? So, okay, here, let me make it a little bit more square. Let's say this is square. So, and I even have some scissors. So, this is not going to be a perfect square, but what if you took this, and you cut out a little square from each side, let's just say, there. And I'll just do one side because I think you'll get it. We won't need to have to watch me take too much time cutting up this. But if you did it on all the sides, I only did it on 2, but pretend like you did it on all the sides. Then they're just going to fold this up right here, okay? They're going to fold that up. And so if you did that on each side, they could fold up all the sides. They'd cut out that little square, and it would form a little box by the time you folded up all of the little sides. And so it's going to make a open top box, okay? And so that is what's happening here. So this is the box they're going to make. When you fold up this side, okay, it's going to eventually make like a little open top box. You can kind of see that. Okay, so so the question is, we don't know how much they're cutting in, but we know that they're going to cut off this much of each side of the box. Okay, so maybe I should just finish that real quick. I did that one side. I would like y'all to be able to see it. So think about this. They said that the side of each box is, originally it's a 3 foot by a 3 foot piece of cardboard. So if you cut out X from each side, we'll have new dimensions once they make that cut. See, this is how it used to be. Let's say this used to be 3, but we put X in here and X in here. And so how much is left right there to make the sides? So here's my little box I just made, like this, okay? How much is left to make that side? Well, if originally it was 3, right here, right? This was 3, then this piece right here is gonna be 3 minus X minus X minus 2X is what's left to make that side. And that's what got folded up, so that means that this dimension right here is 3 minus 2X. it's going to be the same on every side. So that means this dimension right here is 3 minus 2x. And then the height of this box is however high you folded it up, which is however far you cut in, which is known as x. So this is x. So the volume of any rectangular box is length times width times height. So the volume of this guy is going to be 3 minus 2x times 3 minus 2x times x. So let me read the problem again so we can get an idea what's happening. It says a box with an open top, this, is to be constructed from a square piece of cardboard, this, 3 feet wide, by cutting out a square from each of the 4 corners and bending up the sides. Find the largest volume that such a box can have. I guess the constraint is that 3 feet by 3 feet is the amount of material we have. But we could make all kinds of different size boxes depending on how deep we cut in the X. But this will be the dimensions of it. And so what we want to do is, they want the largest volume. We want to maximize this. This is our optimization equation. So it's already all in terms of X, so we didn't have to do that work. Now we need to take the derivative. I'm going to multiply this all together. I think that's the easiest way to take the derivative. So V is a function of X. This is going to be x. I'm going to square this. This is going to be 9 minus 6 minus 12x plus 4x squared. I'm just going to distribute that x. This is 9x minus 12x squared plus 4x cubed. So v prime of x, now we take the derivative, is 9 minus 24x plus 12x squared. Let's set this equal to 0. Let's find the critical value. So when we do this, I'm going to first divide everybody by 3 to make it simpler, because 3 will go into everything. So that's going to be 3 minus 12, no, that's 8, minus 8x plus 4x squared is 0. This is a quadratic equation. And I think it factors. Let me see. Did I do this already? It does factor. It factors into 2x minus 3 and 2x minus 1. And so we get these critical values. X is 3/2, whoops, and x is 1/2. And we need to run a little test and say, well, what's happening at these values? Here's 1/2 and here's 3/2. So we can pick, maybe I'll pick 1/4, and maybe I'll pick 1 for my test value to go in between there, and maybe 2 over there. So here's my test values. Maybe 1/4, maybe 1, and 2. And what we're going to plug this into is the derivative, v prime of x. All right, so when we stick it in here, right here, what are we going to get? All right, 1/4 gives us, this is 9 minus 6. 1/4 is 12 over 16 plus 12 over 16. We get 3 plus a positive number. We get a positive here. This is increasing. All right, when we put in 1 into the derivative, we get 9 minus 24 plus 12. That's 21 minus 24. We get a negative here. This is decreasing. All right. And we put in 3/2, what do we get? 3/2, 2. We put in 2, what do we get here? 9 minus 48. 2 times 2 is 4, 48. We get a positive, so it's increasing. So we find that when we let x be 3/2, we get a minimum. And when we let x be 1/2, we get a maximum. And we want to maximize this. So we should go with, let's let x equal to 1/2 of half a foot. So if x is half a foot, then what is this dimension? 3 minus 2 times 1/2 is 3 minus 1 is 2 feet. That will be this side. So the dimensions that would give the largest volume will be 2 foot by 2 foot by 1/2 foot, and the largest volume would be length times width times height, which is going to be 2 square feet or cubic feet when you multiply all those together. If you were to say, hey, what would happen if I let x be 1/2? It's a little bit silly, because if you let x be, 3/2 at this minimum, it really is a minimum. It's a 0 is what you get there. If you let x be 3/2, -2 times 3/2 is a -3. 3 minus 3 is a 0. The volume would be 0 at that point, so that definitely does give you a minimum. But we want to maximize it, so this is what we should let our dimensions be: 2 by 2 by 1/2 of a foot.